Hello everyone, welcome to my audiobook, and this lesson is from NCERT Chemistry Part 1 Unit 2. This Unit 2 structure of atom is a very lengthy lesson, so I have divided this into two parts. First part is over and this is the continuation of Part 1. So let's start. Explanation of line spectrum of hydrogen. Line spectrum observed in case of hydrogen atom, as mentioned in section 2.3.3, can be explained quantitatively using Bohr's model. According to assumption 2, radiation or energy is observed if the electron moves from the orbit of smaller principal quantum number to the orbit of higher principal quantum number, whereas the radiation is emitted if the electron moves from higher orbit to lower orbit. The energy gap between the two orbits is given by the equation delta E equals to EF minus EI. Combine the equations 2.13 and 2.16. Overall, delta E, what we get is 2.18 into 10 to the power of minus 18 joules of 1 by Ni square minus 1 by Nf square. The frequency V associated with the absorption and emission of the photon can be evaluated by using equation V equals to delta E by H equals to RH by H of 1 by Ni square minus 1 by Nf square. So this overall comes to 3.29 into 10 to the power of 15 of 1 by Ni square minus 1 by Nf square hertz. And in terms of wave numbers equals to V by C equals to RH by HC of 1 by Ni square minus 1 by Nf square. So this, after the calculation, overall we'll get 1.09677 into 10 to the power of 7 of 1 by Ni square minus 1 by Nf square per meter. In case of absorption spectrum, Nf is greater than Ni and the term in the parenthesis is positive and energy is observed. On the other hand, in case of emission spectrum, Ni is greater than Nf, delta E is negative and energy is released. The expression is similar to that used by Rydberg derived empirically using the experimental data available at that time. Further, each spectral line, whether in absorption or emission spectrum, can be associated to the particular transition in hydrogen atom. In case of large number of hydrogen atoms, different possible transitions can be observed and thus leading to large number of spectral lines. The brightness or intensity of spectral lines depends upon the number of photons of same wavelength or frequency observed or emitted. Next, they have given problem 2.10, 2.11. Okay, I will give you the figure of this. Next is limitations of Bohr's model. Bohr's model of the hydrogen atom was no doubt an improvement over Rutherford's nuclear model, as it could account for the stability and line spectra of hydrogen atom and hydrogen-like ions, for example, He plus Li plus 2, Be plus 3 and so on. However, Bohr's model was too simple to account for the following points. First point, it fails to account for the finer details, doublet, that is two closely spaced lines of the hydrogen atom spectrum observed by using sophisticated spectroscopic techniques. This model is also unable to explain the spectrum of atoms other than hydrogen. For example, helium atom which possesses only 2 electrons. Further, Bohr's theory was also unable to explain the splitting of spectral lines in the presence of magnetic field, Zeeman effect, or an electric field, Stark effect. Second point, it could not explain the ability of atoms to form molecules by chemical bonds. In other words, taking into account the points mentioned above, one needs a better theory which can explain the salient features of the structure of complex atoms. Next, 2.5, towards quantum mechanical model of the atom. In view of the shortcoming of the Bohr's model, attempts were made to develop a more suitable and general model for atoms. Two important developments which contributed significantly in the formulation of such a model were: first one, dual behavior of matter; second one, Heisenberg uncertainty principle. First one, dual behavior of matter. A French physicist de Broglie in 1924 proposed that matter, like radiation, should also exhibit dual behavior, that is, both particle and wave-like properties. This means that just as the photon has momentum as well as wavelength, electrons should also have momentum as well as wavelength. De Broglie, from this analogy, gave the following relation between wavelength and momentum of the material particle. Next, Louis de Broglie, 1892 to 1987. Louis de Broglie, a French physicist, studied history as an undergraduate in the early 1910s. His interest turned to science as a result of his assignment to radio communications in World War I. He received his doctorate from the University of Paris in 1924. He was professor of theoretical physics at the University of Paris from 1932 until his retirement in 1962. He was awarded the Nobel Prize in Physics in 1929. So, this is about Louis de Broglie. Okay. Lambda equals to h by mv equals to h by p, where m is the mass of the particle, v its velocity, and p its momentum. De Broglie's prediction was confirmed experimentally when it was found that an electron beam undergoes diffraction, a phenomenon characteristic of waves. This fact has been put to use in making an electron microscope, which is based on the wave-like behavior of electrons, just as an ordinary microscope utilizes the wave nature of light. An electron microscope is a powerful tool in modern scientific research because it achieves a magnification of about 15 million times. It needs to be noted that, according to de Broglie, every object in motion has a wave character. The wavelengths associated with ordinary objects are so short because of their large masses that their wave properties cannot be detected. The wavelengths associated with electrons and other subatomic particles with very small mass can, however, be detected experimentally. Results obtained from the following problems prove these points qualitatively. Next, some problems have been given. Okay, you can check it out. Next, Heisenberg's uncertainty principle. Werner Heisenberg, a German physicist, in 1927 stated uncertainty principle, which is the consequence of dual behavior of matter and radiation. It states that it is impossible to determine simultaneously the exact position and exact momentum or velocity of an electron. Mathematically, it can be given as an equation: delta x into delta px greater than or equals to h by 4 pi, where delta x is the uncertainty in position and delta px is the uncertainty in momentum or velocity of the particle. If the position of the electron is known with high degree of accuracy, delta x is small, then the velocity of the electron will be uncertain. On the other hand, if the velocity of the electron is known precisely, then the position of the electron will be uncertain. Thus, if we carry out some physical measurements on the electron's position or velocity, the outcome will always depict a fuzzy or blurred picture. The uncertainty principle can be best understood with the help of an example. Suppose you are asked to measure the thickness of a sheet of paper with an unmarked meter stick. Obviously, the results obtained would be extremely inaccurate and meaningless. In order to obtain any accuracy, you should use an instrument graduated in its smaller than the thickness of a sheet of the paper. Analogously, in order to determine the position of an electron, we must use a meter stick. calibrated in units of smaller than the dimensions of electron. Keep in mind that an electron is considered as a point charge and is therefore dimensionless. To observe an electron, we can illuminate it with light or electromagnetic radiation. The light used must have a wavelength smaller than the dimensions of an electron. The high momentum photons of such light, P equals to h by lambda, would change the energy of electrons by collisions. In this process, we no doubt would be able to calculate the position of the electron, but we would know very little about the velocity of electron after the collision. Next, significance of uncertainty principle. One of the important implications of the Heisenberg uncertainty principle is that it rules out existence of definite paths or trajectories of electrons and other similar particles. The trajectory of an object is determined by its location and velocity at various moments. If we know where a body is at a particular instant, and if we also know its velocity and the forces acting on it at that instant, we can tell where the body would be sometime later. We therefore conclude that the position of an object and its velocity fix its trajectory. Since for a subatomic object such as an electron, it is not possible simultaneously to determine the position and velocity at any given instant to an arbitrary degree of precision. It is not possible to talk of the trajectory of an electron. The effect of Heisenberg uncertainty principle is significant only for motion of microscopic objects and is negligible for that of macroscopic objects. This can be seen from the following examples. If uncertainty principle is applied to an object of mass, say about a milligram, 10 to the power of minus 6 kg, then delta V into delta x equal to h by 4 pi into m, which gives rise to 10 to the power of minus 28 per meter per second. Okay. So here in a green box they have given about Werner Heisenberg. Okay, let's see. Werner Heisenberg 1901 to 1976. Werner Heisenberg received his PhD in physics from the University of Munich in 1923. He then spent a year working with Max Born at Göttingen and 3 years with Niels Bohr in Copenhagen. He was professor of physics at the University of Leipzig from 1927 to 1941. During World War II, Heisenberg was in charge of German research on the atomic bomb. After the war, he was named director of Max Planck Institute for Physics in Göttingen. He was also accomplished mountain climber. Heisenberg was awarded the Nobel Prize in Physics in 1932. Okay. The value of delta V delta x obtained is extremely small and is insignificant. Therefore, one may say that in dealing with milligram-sized or heavier objects, the associated uncertainties are hardly of any real consequence. In the case of a microscopic object like an electron, on the other hand, delta V into delta x obtained is much larger and such uncertainties are of real consequence. For example, for an electron whose mass is 9.11 into 10 to the power of minus 31 kg, according to Heisenberg uncertainty principle, delta V into delta x equals to h by 4 pi m, which gives rise to 10 to the power of minus 4 m to the power of minus 2 per second. It therefore means that if one tries to find the exact location of the electron, say to an uncertainty of only 10 to the power of minus 8 meter, then the uncertainty delta V in velocity would be 10 to the power of 4 meter per second, which is so large that the classical picture of electrons moving in Bohr's orbits fixed cannot hold good. It therefore means that the precise statements of the position and momentum of electrons have to be replaced by the statements of probability that the electron has at a given position and momentum. This is what happens in the quantum mechanical model of atom. Next, reasons for the failure of the Bohr model. One can now understand the reasons for the failure of the Bohr's model. In Bohr's model, an electron is regarded as a charged particle moving in well-defined circular orbits around the nucleus. The wave character of the electron is not considered in Bohr's model. Further, an orbit is a clearly defined path, and this path can completely be defined only if both the position and the velocity of the electron are known exactly at the same time. This is not possible according to the Heisenberg uncertainty principle. Bohr model of the hydrogen atom therefore not only ignores dual behavior of matter but also contradicts Heisenberg uncertainty principle. So here it is about Erwin Schrödinger, 1887 to 1961. So let's see about him. Erwin Schrödinger, an Austrian physicist, received his PhD in theoretical physics from the University of Vienna in 1910. In 1927, Schrödinger succeeded Max Planck at the University of Berlin at Planck's request. In 1933, Schrödinger left Berlin because of its opposition to Hitler and Nazi policies and returned to Austria in 1936. After the invasion of Austria by Germany, Schrödinger was forcibly removed from his professorship. He then moved to Dublin, Ireland, where he remained for 17 years. Schrödinger shared the Nobel Prize for Physics with P.A.M. Dirac in 1933. In view of these inherent weaknesses in the Bohr model, there was no point in extending Bohr model to other atoms. In fact, an insight into the structure of the atom was needed which could account for wave-particle duality of matter and be consistent with Heisenberg uncertainty principle. This came with the advent of quantum mechanics. Next is quantum mechanical model of atom. Classical mechanics based on Newton's laws of motion successfully describes the motion of all macroscopic objects such as a falling stone, orbiting planets, etc., which have essentially a particle-like behavior as shown in the previous section. However, it fails when applied to microscopic objects like electrons, atoms, molecules, etc. This is mainly because of the fact that classical mechanics ignores the concept of dual behavior of matter, especially for subatomic particles and the uncertainty principle. The branch of science that takes into account this dual behavior of matter is called quantum mechanics. Quantum mechanics is a theoretical science that deals with the study of the motion of the microscopic objects that have both observable wave-like and particle-like properties. It specifies the laws of motion that these objects obey. When quantum mechanics is applied to macroscopic objects for which wave-like properties are insignificant, the results are the same as those from the classical mechanics. Quantum mechanics was developed independently in 1926 by Werner Heisenberg and Erwin Schrödinger. Here, however, we shall be discussing the quantum mechanics which is based on the ideas of wave motion. The fundamental equation of quantum mechanics was developed by Schrödinger and it won him the Nobel Prize in Physics in 1933. This equation, which incorporates wave-particle duality of matter as proposed by de Broglie, is quite complex and knowledge of higher mathematics is needed to solve it. You will learn in solution for different systems in higher classes. For a system such as an atom or the molecule whose energy does not change with time, the Schrödinger equation is written as H. You can see the equation here where H is a schematical operator called Hamiltonian. Schrödinger gave a recipe of constructing this operator from the expression from the total energy of the system. The total energy of the system takes into account the kinetic energy of all the subatomic particles, electrons, nuclei, attractive potential between the electrons and nuclei, and repulsive potential among the electrons and nuclei individually. Solution of this equation gives E and hydrogen atom and the Schrödinger equation. When Schrödinger equation is solved for a hydrogen atom, the solution gives the possible energy levels the electron can occupy and the corresponding wave function of the electron associated with each energy level. These quantized energy states and corresponding wave functions, which are characterized by a set of three quantum numbers: principal quantum number N, azimuthal quantum number L, and magnetic quantum number ML, arise as a natural consequence in the solution of the Schrödinger equation. When an electron is in any energy state, the wave function corresponding to that energy state contains all information about the electron. The wave function is a mathematical function whose value depends upon the coordinates of the electron in the atom and does not carry any physical meaning. Such wave functions of the hydrogen or hydrogen-like species with one electron are called atomic orbitals. Such wave functions pertaining to one electron species are called one-electron systems. The probability of finding an electron at a point within an atom is proportional to the at that point, the quantum mechanical results of the hydrogen atom successfully predict all aspects of the hydrogen atom spectrum, including some phenomena that could not be explained by Bohr's model. Application of Schrödinger equation to multi-electron atoms presents a difficulty. The Schrödinger equation cannot be solved exactly for a multi-electron atom. This difficulty can be overcome by using approximate methods. Such calculations with the aid of modern computers show that orbitals in atoms other than hydrogen do not differ in any radical way from the hydrogen orbitals discussed above. The principal difference lies in the consequence of increased nuclear charge. Because of this, all the orbitals are somewhat contracted further, as you shall see later in subsections 2.6.3 and 2.6.4. Unlike orbitals of hydrogen or hydrogen-like species, whose energies depend only on the quantum number n, the energies of the orbitals in multi-electron atoms depend on quantum numbers n and l. Next is the important features of quantum mechanical model of atoms. So let's see this. Quantum mechanical model of atom is a picture of the structure of the atom which emerges from the application of the Schrödinger equation to atoms. The following are the important features of the quantum mechanical model of atom. First one, the energy of electrons in atoms is quantized, that is, can only have certain specific values. For example, when electrons are bound to the nucleus in atoms. Next, second point, the existence of quantized electronic energy levels is a direct result of the wave-like properties of electrons and are allowed solutions of Schrödinger wave equation. Next, third point, both the exact position and exact velocity of an electron in an atom cannot be determined simultaneously. Heisenberg uncertainty principle. The path of an electron in an atom, therefore, can never be determined or known accurately. That is why, as you shall see later on, one talks of only probability of finding the electron at different points in an atom. Next, fourth point. An atomic orbital is a wave function for an electron in an atom. Whenever an electron is described by a wave function, we say that the electron occupies that orbital. Since many such wave functions are possible for an electron, there are many atomic orbitals in an atom. These one-electron orbital wave functions or orbitals form the basis of the electronic structure of atoms. In each orbital, the electron has a definite energy. An orbital cannot contain more than 2 electrons. In a multi-electron atom, the electrons are filled in various orbitals in the order of increasing energy. For each electron of a multi-electron atom, there shall therefore be an orbital wave function characteristic of the orbital it occupies. All the information about the electron in an atom is stored in its orbital wave function psi, and quantum mechanics makes it possible to extract this information out of psi. The probability of finding an electron at a point within an atom is proportional to the square of the orbital wave function, that is psi square at that point. Psi square is known as probability density and is always positive. From the value of psi square at different points within an atom, it is possible to predict the region around the nucleus where electron will most probably be found. Next is 2.6.1 orbitals and quantum number. A large number of orbitals are possible in an atom. Qualitatively, these orbitals can be distinguished by their size, shape, and orientation. An orbital of smaller size means there is more chance of finding the electron near the nucleus. Similarly, shape and the orientation means that there is more probability of finding the electron along certain directions than along others. Atomic orbitals are precisely distinguished by what are known as quantum numbers. Each orbital is designated by three quantum numbers labeled as N, L, and M, L. The principal quantum number n is a positive integer with value of n equals to 1, 2, 3 goes on. The principal quantum number determines the size and to large extent the energy of the orbital. For hydrogen atom and hydrogen-like species, energy and size of the orbital depends only on n. The principal quantum number also identifies the shell. With the increase in the value of n, the number of allowed orbital increases and are given by n square. All the orbitals of a given value of n constitute a single shell of atom and are represented by the following letters. N equals to 1, 2, 3, 4. Shell is KLMN. Size of an orbital increases with the increase of principal quantum number n. In other words, the electron will be located away from the nucleus. Since energy is required in shifting away the negatively charged electron from the positively charged nucleus, the energy of orbital will increase with increase of n. Azimuthal quantum number. L is also known as orbital angular momentum or subsidiary quantum number. It defines the three-dimensional shape of the orbital. For a given value of n, L can have n values ranging from 0 to n minus 1. That is, for a given value of n, the possible values of L are L equals to 0, 1, 2 goes on to the power. For example, when n equals to 1, value of L is only 0. For n equals to 2, the possible value of L can be 0 and 1. For n equals to 3, the possible L values are 0, 1 and 2. Each shell consists of one or more subshells or sublevels. The number of subshells in a principal shell is equal to the value of n. For example, in the first shell n equals to 1, there is only one subshell which corresponds to L equals to 0. There are two subshells in the second shell, 3 in third shell and so on. Each subshell is assigned an azimuthal quantum number L. Subshells corresponding to different values of L are represented by the following symbols. Value of L 0, 1, 2, 3, 4, 5. Notation for subshell S, P, D, F, G, H. Table 2.4 shows the permissible values of L for a given principal quantum number and the corresponding subshell notation. Okay, you can check it out. Magnetic orbital quantum number ML gives information. Sorry, this might be M. Yeah. Gives the information about the spatial orientation of the orbital with respect to standard set of coordinate axes. For any subshell defined by L value, 2L plus 1 values of ML are possible and these values are given by ML equals to minus L minus L minus 1 minus L minus 2. Thus, for L equals to 0, the only permitted value of ML equals to 0. 1 s orbital. For L equals to 1, ML can be minus 1, 0 and plus 1 equals to 3 p orbitals. For L equals to 2, ML equals to minus 2, minus 1, 0, plus 1 and plus 2 equals to 5. d orbitals. It should be noted that the values of ml are derived from L and that of the value of L are derived from the n. Each orbital is an atom, therefore is defined by a set of values for n, L and m. An orbital described by the quantum numbers n equals to 2, L equals to 1, ml equals to 0 is an orbital in the p subshell of the second shell. The following chart gives a relation between the subshell and the number of orbitals associated with it. Electron spin s. The three quantum numbers labeling an atomic orbital can be used equally well to define its energy, shape and orientation. But all these quantum numbers are not enough to explain the line spectra observed in the case of multi-electron atoms. That is, some of the lines actually occurs in doublets, 2 lines closely spaced, triplets, 3 lines closely spaced, etc. This suggests the presence of a few more energy levels than predicted by the three quantum numbers. In 1925, George Uhlenbeck and Samuel Goudsmit proposed the presence of the fourth quantum number known as the electron spin quantum number ms. An electron spins around its own axis much in a similar way as Earth spins around its own axis while revolving around the Sun. In other words, an electron has, besides charge and mass, intrinsic spin angular quantum number. Spin angular momentum of the electron, a vector quantity, can have two orientations relative to the chosen axis. These two orientations are distinguished by the spin quantum numbers ms, which can take the values of plus half or minus half. These are called the two spin states of the electron and are normally represented by the arrows spin up and spin down. Two electrons that have different ms values, one plus 1 by 2 and the other minus 1 by 2, are said to have opposite spins. An orbital cannot hold more than 2 electrons and these 2 electrons should have opposite spins. To sum up, the four quantum numbers provide the following information. First one, n defines the shell, determines the size of the orbital and also to a large extent the energy of the orbital. Second point, there are n subshells in the nth shell. L identifies the subshell and determines the shape of the orbital. See section 2.6.2. There are 2l plus 1 orbitals of each type of a subshell. That is, 1s orbital L equals to 0, 3p orbitals L equals to 1 and 5d orbitals L equals to 2 per subshell. To some extent, L also determines the energy of the orbital in a multi-electron atom. Third point, M1 designates the orientation of the orbital. For a given value of L, ML has 2L plus 1 values, the same as the number of orbitals per subshell. It means that the number of orbitals is equal to the number of ways in which they are oriented. Next, fourth point. MS refers to orientation of the spin of the electron. Next, shapes of atomic orbitals. The orbital wave function of psi for an electron is an atom has no physical meaning. It is simply a mathematical function of the coordinates of the electron. However, for different orbitals, the plots of the corresponding wave functions as a function of r, the distance from the nucleus, are different. Figure 2.12a gives such plots for 1s n equals to 1, L equals to 0 and 2s n equals to 2, L equals to 0 orbitals. These figures I will provide at the end of this audiobook. You can check it out. According to the German physicist Max Born, the square of the wave function, that is psi square, at a point gives the probability density of the electron at that point. The variation of psi square as a function of r for 1s and 2s orbitals is given in figure 2.12b. Here again, you may note that the curves for 1s and 2s orbitals are different. It may be noted that for 1s orbital, the probability density is maximum at the nucleus and it decreases sharply as we move away from it. On the other hand, for 2s orbital, the probability density first decreases sharply to 0 and again starts increasing. After reaching a small maxima, it decreases again and approaches 0 as the value of r increases further. The region where this probability density function reduces to 0 is called nodal surfaces or simply nodes. In general, it has been found that ns orbital has n-1 nodes, that is, number of nodes increases with increase of principal quantum number n. In other words, number of nodes for 2s orbital is 1, 2 for 3s and so on. These probability density variation can be visualized in terms of charge cloud diagrams. In these diagrams, the density of the dots in a region represents electron probability density in that region. Boundary surface diagrams of constant probability density for different orbitals give a fairly good representation of the shapes of the orbitals. In this representation, a boundary surface or contour surface is drawn in space for an orbital on which the value of probability density psi square is constant. In principle, many such boundary surfaces may be possible. However, for a given orbital, only that boundary surface diagram of constant probability density is taken to be good representation of the shape of the orbital, which encloses a region or volume in which the probability of finding the electron is very high, say 90%. The boundary surface diagram for 1s and 2s orbitals are given in figure 2.13b. One may ask a question, why do we not draw a boundary surface diagram which bounds a region in which the probability of finding the electron is 100%? The answer to this question is that the probability density psi square has always some value, howsoever small it may be, at any finite distance from the nucleus. It is therefore not possible to draw a boundary surface diagram of a rigid size in which the probability of finding the electron is 100%. Boundary surface diagram for a orbital, for a s orbital, is actually a sphere centered on the nucleus. In 2 dimensions, this sphere looks like a circle. It encloses a region in which probability of finding the electron is about 90%. Thus, we see that 1s and 2s orbitals are spherical in shape. In reality, all the orbitals are spherically symmetric. That is, the probability of finding the electron at a given distance is equal in all the directions. It is also observed that the size of the s orbital increases with increase in n. That is, 4s greater than 3s greater than 2s greater than 1s, and the electron is located further away from the nucleus as the principal quantum number increases. Boundary surface diagrams for 3 2p orbitals L equals to 1 are shown in figure 2.14. In these diagrams, the nucleus is at the origin. Here, unlike s orbitals, the boundary surface diagrams are not spherical. Instead, each p orbital consists of 2 sections called lobes that are on either side of the plane that passes through the nucleus. The probability density function is 0 on the plane where the 2 lobes touch each other. The size, shape and energy of the 3 orbitals are identical. They differ, however, in the way the lobes are oriented. Since the lobes may be considered to lie along the x, y and z axes, they are given the designations 2px, 2py and 2pz. It should be understood, however, that there is no simple relation between the values of ml -1, 0 and +1 and the x, y and z directions for our purpose. Next. Okay. For our purpose, it is sufficient to remember that because there are 3 possible values of ml, there are therefore 3 p orbitals whose axes are mutually perpendicular. Like s orbitals, p orbitals increase in size and energy with increase in the principal quantum number, and hence the order of the energy and size of various p orbitals is 4p greater than 3p greater than 2p. Further, like s orbitals, the probability density functions for p orbital also pass through value 0 besides at 0 and infinite distance as the distance from the nucleus increases. The number of nodes are given by the n minus 2. That is, number of radial nodes is 1 for 3p orbital, 2 for 4p orbital, and so on. For L equals to 2, the orbital is known as d orbital, and the maximum value of principal quantum number n has to be 3, as the value of L cannot be greater than n minus 1. There are 5 ml values: minus 2, minus 1, 0, plus 1, and plus 2 for L equals to 2, and thus there are 5 d orbitals. The boundary surface diagram of d orbitals are shown in figure 2.5. The 5 d orbitals are designated as dxy, dyz, dxz, dx square, y square, and dz square. The shapes of the first 4 d orbitals are similar to each other, whereas that of the fifth one, dz square, is different from others, but all 5 3 orbitals are equivalent in energy. The d orbitals for which n is greater than 3 also have shapes similar to 3d orbitals, but differ in energy and size. Besides the radial nodes, that is, probability density function is 0, the probability density functions for the np and nd orbitals are 0 at the plane S passing through the nucleus, that is, origin. For example, in case of pz orbital, xy plane is a nodal plane. In case of dxy orbital, there are two nodal planes passing through the origin and bisecting the xy plane containing z axis. These are called angular nodes, and number of angular nodes are given by L. That is, 1 angular node for p orbitals, 2 angular nodes for d orbitals, and so on. The total number of nodes are given by n minus 1. That is, sum of L angular nodes and n minus L minus 1 radial nodes. Next, energies of orbitals. The energy of an electron in a hydrogen atom is determined solely by the principal quantum number. Thus, the energy of the orbitals in hydrogen atom increases as follows. 1s less than 2s equals to 2p less than 3s equals to 3p equals to 3d less than 4s equals to 4p equals to 4d equals to 4f, and is depicted in figure 2.16. Although the shapes of 2s and 2p orbitals are different, an electron has the same energy when it is in the 2s orbital as when it is present in 2p orbital. The orbitals having the same energy are called degenerate. The 1s orbital in a hydrogen atom, as said earlier, corresponds to the most stable condition and is called the ground state, and an electron residing in this orbital is most strongly held by the nucleus. An electron in the 2s, 2p or higher orbitals in a hydrogen atom is in excited state. The energy of an electron in a multi-electron atom, unlike that of the hydrogen atom, depends not only on its principal quantum number shell but also on its azimuthal quantum number subshell. That is, for a given principal quantum number S, P, D, F all have different energies. Within a given principal quantum number, the energy of orbitals increases in the order S smaller than P, smaller than D, and smaller than F. For higher energy levels, these differences are sufficiently pronounced and staggering of orbital energy may result. Example, 4s smaller than 3d and 6s smaller than 5d, 4f smaller than 6p. The main reason for having different energies of the subshells is the mutual repulsion among the electrons in multi-electron atoms. The only electrical interaction present in hydrogen atom is the attraction between the negatively charged electron and the positively charged nucleus. In multi-electron atoms, besides the presence of attraction between the electron and nucleus, there are repulsion terms between every electron and other electrons present in the atom. Thus, the stability of an electron in a multi-electron atom is because total attractive interactions are more than the repulsive interactions. In general, the repulsive interaction of the electrons in the outer shell with the electrons in the outer shell are more important. On the other hand, the attractive interactions of an electron increases with increase of positive charge on the nucleus. Due to the presence of electrons in the inner shells, the electron in the outer shell will not experience the full positive charge of the nucleus. The effect will be lowered due to the partial screening of positive charge of the nucleus by the inner shell electrons. This is known as the shielding of the outer shell electrons from the nucleus by the inner shell electrons, and the net positive charge experienced by the outer electrons is known as effective nuclear charge. Despite the shielding of the outer electrons from the nucleus by the inner shell electrons, the attractive force experienced by the outer shell electrons increases with increase of the nuclear charge. In other words, the energy of interaction between the nucleus and electron decreases with the increase of atomic number. Both the attractive and repulsive interactions depend upon the shell and shape of the orbital in which the electron is present. For example, electrons present in spherical shaped s orbital shields the outer electrons from the nucleus more effectively as compared to electrons present in p orbital. Similarly, electrons present in p orbital shield the outer electrons from the nucleus more than the electrons present in d orbitals, even though all these orbitals are present in the same shell. Further, within a shell, due to spherical shape of s orbital, the s orbital electron spends more time close to the nucleus in comparison to p orbital electron, which spends more time in the vicinity of nucleus in comparison to d orbital electron. In other words, for a given shell, the experienced by the electron decreases with the increase of azimuthal quantum number L. That is, the s orbital electron will be more tightly bound to the nucleus than p orbital electron, which in turn will be better tightly bound than the d orbital electron. The energy of the electron in s orbital will be lower, more negative than that of p orbital electron, which will have less energy than that of d orbital electron, and so on. Since the extent of shielding from the nucleus is different for electrons in different orbitals, it leads to a splitting of energy levels within the same shell or same principal quantum number. That is, energy of electron in an orbital, as mentioned earlier, depends upon the values of n and L. Mathematically, the dependence of energies of the orbitals on L and n are quite complicated, but one simple rule is that the lower the value of n plus 1 for an orbital, the lower is its energy. If two orbitals have the same value of n plus 1, the orbital with the lower value of n will have the lower energy. The table 2.5 illustrates the n plus 1 rule, and figure 2.16 depicts the energy levels of multi-electrons atoms. It may be noted that different subshells of the particular shell have different energies in case of multi-electron atoms. However, in hydrogen atom, these have the same energy. Lastly, it may be mentioned here that energies of the orbitals in the same subshell decrease with increase in the atomic number. For example, energy of 2s orbital of hydrogen atom is greater than that of 2s orbital of lithium, and that of lithium is greater than that of sodium, and so on. Next, filling of orbitals in atom. The filling of electrons in the orbitals of different atoms takes place according to the Aufbau principle, which is based on the Pauli's exclusion principle, the Hund's rule of maximum multiplicity, and the relative energies of the orbitals. Aufbau principle. The word Aufbau in German means building up. The building up of orbitals means the filling up of orbitals with electrons. The principle states the ground state of the atoms, the orbitals are filled in the order of their increasing energies. In other words, electrons first occupy the lowest energy orbital available to them and enter into higher energy orbitals only after the lower energy orbitals are filled. As you have learnt above, energy of the given orbital depends upon effective nuclear charge, and different type of orbitals are affected to different extent. Thus, there is no single ordering of energies of orbitals which will be universally correct for all atoms. However, following order of energies of the orbitals is extremely useful. The order may be remembered by using the method given in figure 2.17. Okay, this figure of order of filling the orbitals I will be providing you at the end of this audiobook. Starting from the top, the direction of the arrows gives the order of filling of orbitals, that is starting from right top to bottom left. With respect to placements of outermost valence electrons, it is remarkably accurate for all atoms. For example, valency electron in potassium must choose between 3d and 4s orbitals and are predicted by this sequence. It is found in 4s orbital. The above order should be assumed to be a rough guide to the filling of energy levels. In many cases, the orbitals are similar in energy and small changes in atomic structure may bring about a change in the order of filling. Even then, the above series is a useful guide to the building of the electronic structure of an atom, provided that it is remembered that exceptions may occur. Next, Pauli exclusion principle. The number of electrons to be filled in various orbitals is restricted by the exclusion principle given by the Austrian scientist Wolfgang Pauli, 1926. According to this principle, no two electrons in an atom can have the same set of four quantum numbers. Pauli exclusion principle can also be stated as only two electrons may exist in the same orbital and these electrons must have opposite spin. This means that the two electrons can have the same value of the three quantum numbers n, l and ml but must have the opposite spin quantum numbers. The restriction imposed by Pauli's exclusion principle on the number of electrons in an orbital helps in calculating the capacity of electrons to be present in any subshell. For example, subshell 1s comprises one orbital and thus the maximum number of electrons present in 1s subshell can be 2. In p and d subshells, the maximum number of electrons can be 6 and 10 and so on. This can be summed up as the maximum number of electrons in the shell with principal quantum number n is equals to 2n square. Next is Hund's rule of maximum multiplicity. This rule deals with the filling of electrons into the orbitals belonging to the same subshell, that is orbitals of equal energy called degenerate orbitals. It states pairing of electrons in the orbitals belonging to the same subshell p, d or f does not take place until each orbital belonging to that subshell has got one electron each, that is it is singly occupied. Since there are 3p, 5d and 7f orbitals, therefore the pairing of electrons will start in the p, d and f orbitals with the entry of 4th, 6th and 8th electron respectively. It has been observed that half-filled and fully filled degenerate set of orbitals acquire extra stability due to their symmetry. Next, electronic configuration of atoms. The distribution of electrons into the orbitals of an atom is called its electronic configuration. If one keeps in mind the basic rules which govern the filling of different atomic orbitals, the electronic configuration of different atoms can be written very easily. The electronic configuration of different atoms can be represented in two ways. For example, S, A, P, B, D, C notation. Second one, orbital diagram. In the first notation, the subshell is represented by the respective letter, symbol and the number of electrons present in the subshell is depicted as a superscript like A, B, C, etc. The similar subshell represented the different shells is differentiated by writing the principal quantum number before the respective subshell. In the second notation, each orbital of the subshell is represented by a box and the electron is represented by the arrow, a positive spin or an arrow of negative spin. The advantage of the second notation over the first is that it represents all the four quantum numbers. The hydrogen atom has only one electron which goes in the orbital with the lowest energy, namely 1s. The electronic configuration of the hydrogen atom is 1s1, meaning that it has one electron in the 1s orbital. The second electron in helium can also occupy the 1s orbital. Its configuration is Therefore, 1s2. As mentioned above, the two electrons differ from each other with opposite spin, as it can be seen from the orbital diagram. The third electron of lithium is not allowed in the 1s orbital because of Pauli exclusive principle. It therefore takes the next available choice, namely the 2s orbital. The electronic configuration of Li, that is lithium, is 1s2 2s1. The 2s orbital can accommodate one more electron. The configuration of beryllium atom is therefore 1s2 2s2. In the next 6 elements, boron, carbon, nitrogen, oxygen, fluorine and neon, the 2sp orbitals gets progressively filled. This process is completed with the neon atom. The orbital picture of these elements can be represented as follows. You can check it out. The electronic configuration of the elements of sodium 1s2, 2s2, 2p6, 3s1 to argon 1s2, 2s2, 2p6, 3s2, 3p6 follow exactly the same pattern as the elements from the lithium to neon, with the difference that the 3s and 3p orbitals are getting filled now. This process can be simplified if we represent the total number of electrons in the first two shells by the name of the element neon. The electronic configuration of the elements from sodium to argon can be written as Ne, okay, sodium to neon. The electrons in the completely filled shells are known as core electrons, and the electrons that are added to the electronic shell with the highest principal quantum number are called valency electrons. For example, the electrons in neon are the core electrons and the electrons from sodium and argon are the valency electrons. In potassium and calcium, the 4s orbital, being lower in energy than the 3d orbitals, is occupied by 1 and 2 electrons respectively. A new pattern is followed beginning with scandium. The 3d orbital, being lower in energy than the 4p orbital, is filled first. Consequently, in the next 10 elements, scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper and zinc, the 5 3d orbitals are progressively occupied. We may be puzzled by the fact that chromium and copper have 5 and 10 electrons in 3d orbitals rather than 4 and 9, as their position would have indicated with 2 electrons in the 4s orbital. The reason is that fully filled orbitals and half-filled orbitals have extra stability, that is lower energy. Thus, P3, P6, D5, D10, F7, F14, etc. configurations which are either half-filled or fully filled are more stable. Chromium and copper therefore adapt the D5 and D10 configuration. With the saturation of the 3d orbitals, the filling of the 4p orbital starts at gallium and is complete at krypton. In the next 18th element, from rubidium to xenon, the pattern of filling the 5s, 4d and 5p orbitals are similar to that of 4s, 3d and 4p orbital as discussed above. Then comes the turn of the 6s orbital. In cesium and barium, this orbital contains 1 and 2 electrons respectively. Then from lanthanum to mercury, the filling up of electrons takes place in 4f and 5d orbitals. After this, filling of 6p, then 7s and finally 5f and 6d orbitals takes place. The elements after uranium are all short-lived and all of them are produced artificially. The electronic configuration of the known elements as determined by spectroscopic methods are tabulated in table 2.6. One may ask, what is the utility of knowing the electron configuration? The modern approach to the chemistry, in fact, depends almost entirely on electronic distribution to understand and explain chemical behavior. For example, questions like why two or more atoms combine to form molecules, why some elements are metals while others are non-metals, why elements like helium and argon are not reactive but elements like the halogens are reactive, Find simple explanation from the electronic configuration. These questions have no answer in the Daltonian model of atom. A detailed understanding of the electronic structure of atom is therefore very essential for getting an insight into the various aspects of modern chemical knowledge. Next, stability of completely filled and half-filled subshells. The ground state electronic configuration of the atom of an element always corresponds to the state of the lowest total electronic energy. The electronic configuration of most of the atoms follow the basic rules given in section 2.6.5. However, in certain elements such as copper or chromium, where the two subshells 4s and 3d differ slightly in their energies, an electron shifts from a subshell of lower energy 4s to the subshell of higher energy 3d, provided such a shift results in all orbitals of the subshell of higher energy getting either completely filled or half filled. The valency electronic configurations of chromium and copper therefore are 3d5 4s1 and 3d10 4s1 respectively, and not 3d4 4s2 and 3d9 4s2. It has been found that there is extra stability associated with these electronic configuration. Causes of stability of completely filled and half-filled subshells. The completely filled and completely half-filled subshells are stable due to the following reasons. First one, symmetrical distribution of electrons. It is well known that symmetry leads to stability. The completely filled or half-filled subshells have symmetrical distribution of electrons in them and are therefore more stable. Electrons in the same subshell, here 3D, have equal energy but different spatial distribution. Consequently, their shielding of one another is relatively small and the electrons are more strongly attracted by the nucleus. Next, second point, exchange energy. The stabilizing effect arises whenever two or more electrons with the same spin are present in the degenerate orbitals of the subshell. These electrons tend to exchange their positions and the energy released due to this exchange is called exchange energy. The number of exchanges that can take place is maximum when the subshell is either half filled or completely filled. As a result, the exchange energy is maximum and so is the stability. You may note that the exchange energy is at the basis of Hund's rule that electrons which enter orbitals of equal energy have partial spins as far as possible. In other words, the extra stability of half-filled and completely filled subshell is due to, first point, relatively small shielding, second point, smaller Coulombic repulsion energy, and third point, larger exchange energy. Details about the exchange energy will be dealt with in higher classes. So, possible exchange, okay, here they have given figures, you can check it out. Next is the electronic configuration of the elements. Okay, table 2.6. This one I will be giving you at the end of this audiobook. You can check it out. Okay. And next, okay, all the elements electronic configuration has been given. Yeah, so with this we are done with the lesson. Next is the summary. Atoms are the building blocks of elements. These are the smallest parts of an element that chemically react. The first atomic theory proposed by John Dalton in 1808 regarded atom as the ultimate indivisible particle of matter. Towards the end of the 19th century, it was proved experimentally that atoms are divisible and consist of three fundamental particles: electrons, protons, and neutrons. The discovery of subatomic particles led to the proposal of various atomic models to explain the structure of the atom. Thomson in 1898 proposed that an atom consists of a uniform sphere of positive electricity with electrons embedded into it. This model, in which mass of the atom is considered to be evenly spread over the atom, was proved wrong by Rutherford's famous alpha particle scattering experiment in 1909. Rutherford concluded that atom is made of a tiny positively charged nucleus at its center with electrons revolving around it in circular orbits. Rutherford's model, which resembles the solar system, was no doubt an improvement over Thomson's model, but it could not account for the stability of the atom. That is why the electron does not fall into the nucleus. Further, it was also silent about the electron structure of atoms, that is, about the distribution and relative energies of electrons around the nucleus. The difficulties of Rutherford model were overcome by Niels Bohr in 1913 in his model of the hydrogen atom. Bohr postulated that electron moves around the nucleus in circular orbits. Only certain orbits can exist and each orbit corresponds to a specific energy. Bohr calculated the energy of electron in various orbits and for each orbit predicted the distance between the electron and nucleus. Bohr model, though offering a satisfactory model for explaining the spectra of the hydrogen atom, could not explain the spectra of multi-electron atoms. The reason for this was soon discovered. In Bohr model, an electron is regarded as a charged particle moving in a well-defined circular orbit about the nucleus. The wave character of the electron is ignored in Bohr's theory. An orbit is a clearly defined path, and this path can completely be defined only if both the exact position and the exact velocity of the electron at the same time are known. This is not possible according to the Heisenberg uncertainty principle. Bohr model of the hydrogen atom therefore not only ignores the dual behavior of the electron but also contradicts Heisenberg uncertainty principle. Erwin Schrödinger in 1926 proposed an equation called Schrödinger equation to describe the electron distributions in space and the allowed energy levels in atoms. This equation incorporates de Broglie's concept of wave-particle duality and is consistent with Heisenberg uncertainty principle. When Schrödinger equation is solved for the electron in a hydrogen atom, the solution gives the possible energy states the electron can occupy and the corresponding wave functions, psi, which in fact are the mathematical functions of the electron associated with each energy state. The quantized energy states and corresponding wave functions, which are characterized by a set of three quantum numbers, principal quantum number n, azimuthal quantum number L, and magnetic quantum number ml, arise as a natural consequence in the solution of the Schrödinger equation. The restrictions on the values of these three quantum numbers also come naturally from this solution. The quantum mechanical model of the hydrogen atom successfully predicts all aspects of the hydrogen atom spectrum, including some phenomena that could not be explained by the Bohr's model. According to the quantum mechanical model of the atom, the electron distribution of an atom containing a number of electrons is divided into shells. The shells in turn are thought to consist of one or more subshells, and subshells are assumed to be composed of one or more orbitals which the electrons occupy. While for hydrogen and hydrogen-like systems such as He plus, Li plus 2, etc., all the orbitals within a given shell have same energy. The energy of the orbitals in a multi-electron atom depends upon the values of n and L. The lower the value of n plus 1 for an orbital, the lower is its energy. If two orbitals have the same n plus 1 value, n plus L value, the orbital with the lower value of n has the lower energy. In an atom, many such orbitals are possible and electrons are filled in those orbitals in order of increasing energy in accordance with Pauli exclusion principle. No two electrons in an atom can have the same set of four quantum numbers, and Hund's rule of maximum multiplicity, pairing of electrons in the orbitals belonging to the same subshell, does not take place until each orbital belonging to that subshell has got one electron each, that is singly occupied. This forms the basis of the electronic structure of atoms. So with this we are done with the lesson. If you like my audiobook, please share it to your friends, like and subscribe. If you have any suggestions, please post it in the comment box. Thank you.